Our team worked with GE on their non-optical flame detection algorithm. GE is one of the world's leaders in gas turbines, and that their turbines supply electricity to millions of people worldwide. The objectives for this project was with the gas turbines sometimes losing flames. If the turbine doesn't turn off when the flame is lost, those turbines can go blow up. So it's very important to have a system in place that would turn off the turbine when the flame was lost. Their current system is using cameras inside of the turbine, which have to be water cooled, but those can malfunction and cause expensive shutdowns. What we're helping with is their algorithm to detect flame state without having to have a sensor inside of the turbine itself. It's currently a pass or fail, and in this project we work to define a continuous margin. The first thing we did in this project was work through the current algorithm to understand how it worked, and then we updated the margin equations and removed the discontinuities, and then verified that the new margin calculations fix the problems that existed with the previous version of the algorithm. This is a block diagram of our parallelization of the algorithm that we deemed necessary for testing purposes to process large amounts of data. This is a block diagram of the margin calculation that will be important going forward to get to testing how changes in the margin affects the overall performance of the system. We worked to run at least 4 cases simultaneously on our machines, and we worked to fix all the cases that defaulted to 99 margin, and we define them to have a more continuous margin.
Thank you. So this is an overview of the non-optical flame detection, the GENOFD algorithm. It takes in a bunch of signals like temperature and pressure from the turbine, processes them, and then aggregates them to predict whether the flame is lit or not lit. One issue that previous attempts to define a margin had was that if you're thinking about time margins, there's 2 kinds. There's first TM1, which is, did you trigger earlier than you had to? So if you had 1.5 seconds to trigger, did you trigger in 1 second? Additionally, the GENOFD algorithm requires 2 separate signals to signal loss of flame to actually say that there was a loss of flame. So temperature and pressure, for example, would have to trigger at the same time. That's TM2. It's that, did you have that time overlap between your signals? One issue was that if a signal failed to trigger, if temperature just never crossed the thresholds it needed to, the GE system was to set both of those time margins to -99. This resulted in issues. For example, on this graph on the bottom here, as you slightly change the thresholds, the margin changes dramatically. This is terrible for if you're trying to optimize the GENOFD system based on this margin calculation. To fix this, we updated that code to be more realistic about what was really going on. Here is our visualization of our solution. I'm going to focus on this bottom left graph here, where we have the actual value of temperature in purple, the derivative of temperature, and this dotted black line, and the trigger value in this blue. So here we can see that from about 8 seconds to 9 seconds, temperature did trigger and say there was a loss of flame. If it didn't, though, if it didn't get above the thresholds that it needed to, we placed a ghost trigger, which you can imagine is just a very thin blue spike right here that says that's where we triggered, or that's where we would have triggered if we got above those thresholds. We figure out the location of that ghost trigger by looking at the global minimum of the second derivative. This change makes our time margins much more continuous. Even if we don't trigger, we still get some useful information based off of where the ghost trigger would have been. Even in our overlaps, we can still kind of tell, okay, if this signal did trigger, roughly how much overlap would there have been and how much distance was there between our signals. This does solve the issue. We have that same graph from before with the thresholds on temperature on the x-axis and the margin on the y. In the old system, there was a dramatic drop in margin for a slight change in the threshold. Now we have a much more smooth transition, which is great for optimization and improving those parameters. And here we have a similar graph just for the TM2, the overlap between signals. We go from a crazy drop to now a much more reasonable drop in those time margins. To evaluate this, we made a parallel implementation of our work in Python. It's difficult to install on a distributed computing system, but it can be installed using pip for the newest versions of MATLAB. Our results from this, where we ran all the new margin calculation on 1,000 cases, and you can see where the old margin would predict 99. We had a bunch of cases, all bunched up at 99, that we redistributed to different margins. So now we have a bunch of cases that were just set to 99 by default that we've assigned meaningful margin to. It's actually going to mean something now instead of just 99. We have a couple examples where we searched out the old margin and the new margin. And you can see that the new margin is dramatically different even from each other. So we did actually provide more meaning here.
So some of the challenges that we had as a group was to understand the structure of the non-optical flame detector and how things were calculated. Also, the main thing was figuring out how deep into the code we needed to do. In doing that, it took quite a while to figure out about doing it, especially looking at someone else's code and trying to figure out how to improvise it to make it better. The hurdles that we went through was reducing the discontinuity in the margins and also running the driver in parallel. Most of these challenges were difficult in the beginning, but as time went on and diving deeper into the code, the goal of getting this task done became much more clear. The three main things that slowed us down were understanding the code that GE engineers wrote before, figuring out how to change the margin calculations so that we get more prompt trigger. And the technical issues we had were just figuring out how to use parallelization in the code. Going forward, I believe that future teams won't have to dive as deep into the code to figure out margin calculations, because what we did was very sufficient. And also for future teams, MATLAB code on the cluster would probably have to be updated to a newer version in order to run parallelization implementations to make things much more easier.
For future work, we understand that our solution is not a perfect solution. For example, some difficulties are when your derivatives look like this, so they cross below the threshold multiple times. And that can make our solution behave a little strangely. It's not identical to what would have happened, but it's much closer than just assuming -99. An additional factor is how we compare time margins to value margins. We talked about those less, but those are how far above or below our signal gone above its threshold. There's a weird scaling factor here that we have to consider. If it's too low, then all we see is time margin. And if it's too high, then time margin is just not considered. We also have a list of files for future teams. If you want to know where things are located, this describes how the files are distributed. And our long-term goals for this project would be to calculate the gradient of the new margin with respect to all of the parameters we have, and then to use that to optimize those parameters to increase this non-optical flame detection algorithm performance. I'd like to take a second to appreciate General Electric for giving us the opportunity and the data to help solve this problem. And then a big thank you to Dr. Healy, Dr. Groff, and Dr. Raza for providing guidance for the duration of the project. Thank you.